Hey. Pouring like a blaze.
Okay, so can you guys hear me right now? If so, just send me a message in either of the chats. If you can hear me, and then I'll speak to you. Okay, I mean, can you guys hear my audio from the YouTube video? Okay, so what I was gonna say is that I want to keep the VC open so that at any moment anyone can just unmute themselves and say anything that they have like as a question or anything, because usually I don't the YouTube live stream is like muted. There's no way for me to communicate because I'm not looking at Discord the entire time. So it's best if you tell me ask any question through the VC at any point. And yeah, that's why I do that. But otherwise, I use exclusively the YouTube live stream. Okay, I'll start in like 5 minutes and wait for people to come. And see if people do come. Okay, I'm just gonna start the session now because I don't think there's gonna be that many more people, and I'm already running really late. So here we go. Um, okay, first thing in calculus is limits. Um, and the concept of limits is important because let's go into this. Did update? Interesting. Well, the concept of limits is basically trying to identify the value of the function while it approaches any given value, which is usually what one would do if the function is approaching different values when you're coming from different directions, or if you evaluate at different intervals. So, an example of something like this, where limits would be useful, is if you had a function that looked like this, um, and like that. So. Could you mute yourself? Wait. Can you mute yourself? Whoever you are. Okay, just okay. He left. Okay. Okay. That's okay. Uh, just stay muted. Okay. So if you have something like this, what this actually represents is that you're approaching this value from this direction. There's a jump, and then you're approaching from this direction. So a limit would be useful over here because you can identify the limit coming in from this direction and the limit coming in from this direction. So for example, for this sum function, let me call this function f of x, and let me call this point 3, and this point is 1, and this point is 2. So the limit of f of x as x approaches 3 from the positive direction, which is from the right, is equal to 2. But the limit as f of x approaches x approaches 3 from the negative direction is going to be equal to 1, which is from the left direction. And this is basically what the limit is like equipping us to do. And it's to look at like the values like this, and eventually this is like helping us. This also leads very nicely into a definition of continuity for HL, which is basically saying that is this function continuous, and this function can only be continuous if the limit of f of x from x approaching 3 from the positive direction is equal to the limit of f of x approaching 3 from the negative direction. So this is also very important, and that's definitions of continuity. Now limits can also be used when you're trying to approach a certain value, but you can't evaluate at that value. So again, over here you could evaluate f of x at 3, and you would get 2 because that's where the hole over here is shaded in. However, there's always like cases where you can't do that. And limits come in very handy, especially when you're trying to calculate the derivatives. So just really quickly, I'll come up with the derivation of the derivative. Which is I always find useful to do. Say you have in any given curve, you want to be able to find what the slope is of that curve at any given point. So you can graph one point on that curve, say x, and you know that the y value for that curve is going to be f of x at that point. Then you take some value, x plus h, which is there's a h distance from x. And that's going to be evaluated as f of x plus h. That's going to be f of x plus h when evaluated for this function. Just label the function f of x. And this gives us the tools to look at a slope. So if we wanted to look at what the slope of this curve was, it would be a slope of a line between these 2 points is going to be f of x plus h minus f of x, which is the difference in the y values right there, over the difference in the x values, which is x plus h minus x, which we know is h. And then but obviously what we want to try and find out is the slope given at any point x. The best way to do this is if h was 0. That would mean that the line is exactly at x and completely tangent to x. However, we can't do that because notice that we have a h in the denominator, which means if we set h equal to 0, this is going to be indeterminate. It's going to be infinity, which means we cannot evaluate it. So that's why we always make sure we put in a limit as x approaches h. So what this lets us do, as I mean, not as x approaches h, as h approaches 0. And what this lets us do is it lets us evaluate the limits so that we can calculate exactly what the tangent is going to be by looking at the slope definition. And then once evaluated, we're able to find what the derivative is. And this is the fundamental definition of the derivative, which is, it's neat to know. And that's just the reason. Okay, let me look at what they're saying in the chat. You could also just VC this, because I don't actually look at the chat very often. That's not right now. Yes, that is. Yes, that's true. Yeah, what Redstone Technique said is correct. When you're looking at the limit definitions of looking at a function, you need to make sure that not only does the if you want to check for continuity, you need to check that it's from the left direction. It is equal to the same thing as from the right direction, and it's also equal to the function itself. So what that means, let me just explain what he said over there. What that means is this. Means that if you have any given function, from the earlier definition that I gave, say this is what the function looked like, and there's a point up there. From the earlier definition I gave, this would have been continuous, but obviously it's not continuous because there's a hole over here. So you need to make sure that the limit as f of x, limit of f of x as x approaches some value from the positive direction is equal to the limit of f of x as x approaches a from the negative direction, and that's also equal to f of a. So all these things need to be met in order for continuity to exist, and this is HL. This is HL content. Unless an SL student has learned this and I'm just confused, but I'm pretty sure the continuity is HL. So yeah, thanks Redstone. What's next? First principle, derivative change, increasing, decreasing functions. Okay, so the next things that we need to discuss is the trying to identify critical points in a function. And the way that we actually try and find critical points in a function is by looking at their derivatives and their second derivatives. So you could have all kinds of functions. So actually, I think I'm going to just pop in a Desmos and use the graph ringer instead. So let's see, x squared. Let's try this. Why does this look like this? Okay, interesting. There we go. Nice. Much nicer. So what are the different critical points for this function? Just select it. Okay, so what are the different critical points for this function? Now, there are a list of different kinds of critical points. So the first of these critical points, let me actually just snip. Okay, so the first of the critical points is maximums. So maximums, right? Maximums are the first kind of critical points. However, the maximums can be divided into two different kinds of maximum. There are local maximum and there are global maximum. And what that means, so what the maximum really means in the function is what is the highest value the function can go to. Now there are local maximum and there are global maximum. Global maximum is that across all points, what is the highest point it can go to. So for this function, x cubed minus 10x minus 5, it's clear to see that the maximum of this function could be infinity. For any given value, if I put a large enough number, it's going to hit infinity. So that's a global maximum. However, locally there are maximums as well. So as you can see right over here, there's a maximum point right over there, which is also significant, and that's a local maximum because it's only a maximum for that for its region and in that specific area, not for the entire function. So the maximum for the entire function is the global maximum, and the maximum for this area is the local maximum. And the same thing can be said for minimums, which can be local or they can be global. And so if you, as you can see, this was where the global maximum was, but this is where the global minimum is. It can be go to negative infinity. However, there's also the local minimum right over here, which is that this is the minimum point for this specific region. Now, it's important to be able to figure out what these maximums and minimums are, and the way that you're able to find what these maximums and minimums are is by analyzing the first derivative. And the reason why we would analyze the first derivative in this situation is specifically because the first derivative holds information regarding the slope of this function, and you need to be able to utilize that information. And the way that that's done is by just noticing what's happening to the function at any given point over here. Yeah? Yes? Did anyone say anything? I heard a hello and then just nothing. The link. Just scroll up. The link is there. Oh. Okay, cool. I'm going to continue. By looking at what's happening to the slope as it reaches this maximum, as it reaches the minimum, and then we can use those techniques for further afterwards. So, as you're approaching this maximum, the slope is very, very steep. The function is very steep. It's extremely steep in this direction, and then it slowly flattens out, eventually until it hits horizontal, and then becomes negative again. So, if we were to look at what the derivative would be doing at the point where this maximum occurs, you know that it's going to be giving a maximum when the derivative is equal to 0, specifically a local maximum, when the derivative is equal to 0. So when the derivative is equal to 0, it's going to be flat, horizontal, which means you're going to be having a maximum. However, there's a little problem with this theory. If we're looking at what happens as we're going downwards towards the local minimum, it's very steep downwards, right? And it starts flattening out, becomes horizontal, then becomes steep upwards again. However, the issue with this is that when the derivative, again, is equal to 0 at this point, with a horizontal line. But the way that we can fix that, the problem is that the maximums occur when the derivative is equal to 0, but the minimums also occur when the derivative is equal to 0. So you need to find a way to be able to distinguish when does the derivative, when is there a maximum and when is there a minimum. And there's two ways we can do that. First of all, you can try and look at what's happening to the derivative very close to the function and around it. So for example, you know that if you calculate what the derivative is, just to the left of this. So I know that this looks around about 1. It looks like this slope is happening around 1. I didn't check correctly, but it looks like it's happening at around x equals to 1. But so you can check what happens at x equals to like negative 1.5 and x equals to 0. And if it's going to be if the derivative is going to, so if you're looking at like a sine chart. Right, so if we're going to look at when it equals to 0, so the derivative is equal to 0 at 2 points. I'm going to call this point x equals to negative 1, and I'm going to call this point x equal to positive 1. It's not these values. I'll find these values later, but I'm using this just for the sake of explanation. So at negative 1 it hits a 0, and at positive 1 it hits a 0. But you want to know whether it's a maximum or minimum. Now, we've already graphed it, so we know that it's a maximum or minimum. But the way we can do this is we can look at all the other values around of the derivative. So if we evaluate negative 1, it's a 0, and if we evaluate 1, it's also a 0. But we can look at the value of the derivative at other points. So for example, we can figure out what the derivative of this is, which is going to be 3x squared using a normal power rule. So that's 3x squared, and then minus 10x is going to give us minus 10, and that's what the derivative is. The negative 5 disappears when you take the derivative. So 3x squared minus 10. We can look what happens right to the left of it. So let's look at what happens at negative 2. At negative 2, what is the value? If you plug in negative 2 into this, you're going to get 3 times negative 2 squared minus 10, which is going to be equal to 3 times 4, which is 12, minus 10, which is equal to 2. So you know, again, that there's going to be a positive slope. So you know that the slope is positive over here. Then you can check in the middle between the two of them. And the way we can do that is plug in the value 0, which is in the middle of 1 and negative 1. So plug in 0, and you see that it's going to give you 3 minus 10, which is negative 7. So again, you know there's negative values in here. Then again, following the same procedure, find some value towards the right of 1 and check what the derivative is equal to at those points. And you see that it's all equal to pluses. And that's why, and so now what you notice is that the change in sign indicate is that there's an increase up to that point, and then there's a negative value. So there's a positive slope going upwards, and then it starts dropping back down. So you know that there's going to be a maximum at right at this point. And this is how you analyze a function to see whether or not it's a maximum or a minimum, by looking at this sign change and how it's happening, and just thinking about what is happening in terms of a slope. So you know this is going to be a maximum because this is a negative, and then going positive, you know that this is going to be a minimum. Something that's even more important is that sometimes you could end up with having a derivative equal to 0, but this is what happens. If you're looking at a sign chart for some, say some random value a, for some random function, right? And you know it's equal to 0 at this point. It's positive on the left of a, but it's also positive on the right of a. And now this is very important because you should be checking for this, and to check whether or not there's actually a maximum or minimum, because it's very possible there couldn't be one. And this is exactly the case for the function x cubed, which I can show you right now. The function x cubed, which looks like this. If you look at the function x cubed closely, you can see that there is a horizontal slope right over here, but there is no maximum and no minimum. This is very important, and you should be able to identify when this occurs. Now, now I said that there were two ways to figure out whether or not there's a maximum or a minimum, and the other way to do this is to look at something called the concavity of the function. No, not the whiteboard. No, not the keyboard. No, not the keyboard again. And the concavity basically says what kind of shape does the function have at any given point. So we know that this has a derivative equal to 0, and we know this point has a derivative equal to 0. But how do we check whether those are maximums or minimums? And the way we can do that is by looking at the concavity. So when you have concavity measures is the change in slope. So it's the derivative of the derivative, which means that concavity corresponds to the second derivative. It corresponds to the second derivative, and it measures the change in slope. So if you have a positive concavity, what that means is that your slope is increasing. So that means that if you have like a negative slope and then it's slowly becoming positive, and then it hits 0 and then eventually it becomes positive, that means you have a positive concavity. What that corresponds to is a happy face, which is like that. It's positive concavity. Positive concavity. It has a happy face. You could have a negative concavity, which means that it's getting smaller and smaller. So you could have a very steep slope, and then you eventually hit 0, and then you start going negative again. And that's negative concavity, which is a sad face, like this. Now the quick way for you to check whether or not this, each point which you suspect is a maximum or minimum, is by looking at the concavity at that point. Because if you have a positive concavity, you know that this point is occurring in a region where there's a happy face, like this, which means that it's going to be a minimum. Or you can look at if you had a region where it's a negative concavity, you know it's a sad face, which means there's going to be a maximum at that point. So this is how you can figure out. So you can check whether or not something's a maximum or minimum by looking at the second derivative's value at any given point. So that's how those are the way you check. So if you have suspected values for when the derivative is equal to 0, right? X1, x2, you look at what f of the second derivative of f of x1 is, and the second derivative of f of x2 is, and you check what their sign is. And that's what it's going to explain to you what the concavity is at this point. Now this is the second way that you could do it, and this is obviously the previous way, which is looking at the sign changes, and that is equally okay as well. That's perfectly fine as well. That's okay to use. So yeah, these are techniques. Now this brings to mind another thing that's relevant regarding concavity, which is of the final critical point. So we looked at maximums, we looked at minimums, but now we're going to look at inflection points. So inflection points are the final things you're going to have to ever calculate for the inflection point. This is when there's a change in concavity. A change in concavity. So that basically means, when does it change from a sad face to a happy face, basically. I'm a kid when it comes to coming up with math logic, so I use happy face and sad face, but it's okay. Um, so when does that change occur? So if you can look at this function, you can see just like generally where it's going to be, because you can see it's like a sad face here, like around here, but it then eventually hits to be a like it becomes a sad, like a happy face back over here, like it becomes like a positive concavity again. So you know it's somewhere around here there's a change, and that change is called the inflection point, which is very important. And it needs to be a change from positive to negative. Now the way you can check for this is when does the second derivative equal to 0? That's when there's going to be an inflection point for the function. So looking at where the second derivative is going to be, you'll know that there's going to be a change from positive to negative. However, you cannot assume there's going to be a change from positive to negative or a change from negative to positive. It's very probable the function is positive concavity, hits 0, and then continues to be positive concavity, which is not the case over here. However, it could be the case, and it is the case for another function, x cubed. Right over here. Wow, x cubed really is a wonderful example. As you can see over here, oh wait, there is a change in this one. This changes it. There's also places where there's no changes. Like over here, I can't come up with an example off the top of my head, but it's very probable that you have a there's a possibility that whatever your inflection point is, it's going to be what you suspect to be an inflection point isn't actually an inflection point. So it's important that you check on the right and you check on the left whether or not it's actually there. So what you should do is, again, you should draw a sign diagram. You should draw a quick sign diagram and check whatever point. Say you have a point x, right, and you found that it is equal to 0. At f of x is going to be equal to 0. So you can just check whether it's positive on this side. If it's positive on this side, if it's both positive, then it's not an inflection point. There needs to be a change in sign, and you need to make sure that you check for this. Now, for SL, this is going to be very simple. The functions, generally, you can sketch it, and you can possibly just figure out you'll figure out all the everything you need to know just from a simple sketch. I very strongly urge you, if it is sketchable, if it's like a very simple polynomial, please draw a sketch, think about what it's going to be. You'll be able to much better understand and solve the problem. And for HL, it's very probable you're going to get dead. Nice. For HL, there's probably going to be a lot harder content for inflection points, so you will have to be testing the points to left and right if at that stage. And if it gets too complicated, you'll have to know how to use it with your calculator. And that brings me to another point. Your calculator is also able to analyze for critical points, so make sure that for whatever calculator you have, you're able to do this for paper 2. So on my TA Inspire, I'm able to analyze the function to check for a 0, which is just like the 0 over here, right? But you can also check for zeros of the second derivative. So if you have like a complex function, and you want to figure out when does the second derivative equal to 0, you can plug it in and use your calculator to do that. For the original function, you're also able to look at the minimum, you're able to look at the maximum. And I think that's all your calculator is able to do. The inflection points you need to be able to do on your own. So make sure you're able to do that. Very important you know how to use your calculator correctly. It's immensely important. Could save you a lot. So that's that. Yep, covered everything. And I think I'd covered the graphical behavior. And for HL, you should be able to find higher derivatives. What this basically means is that a lot of the times in questions, they're going to ask you to derivate something several times. They're just keep asking you to differentiate it. And yeah, so that's kind of what that means. Now for both SL and HL, you should be able to differentiate almost every function. However, I find that it's more important that you're able to understand just how to do it rather than memorizing everything, because at the end of the day, you have this big formula booklet which has everything in it, everything you need to know. And I think SL has the exact same thing. It's everything you need to know. You have it in here. Now, it comes down to making sure that you understand what these things mean and that you understand what you're doing when you do this. and they understand the procedures that are used when you want to use these rules over here. And most important, so that brings me most important to the product, quotient, and chain rule. You should be very comfortable with using these. Do a lot of practice with this. Obviously, I don't even know if I can advertise the question banks. Whatever resources you have, you should definitely practice product and chain rules. I might give some examples later in the session as well. But you should be able to understand what is happening even in the formula booklet, because truly, if you understand every formula in the formula booklet, it's very hard to not know how to do a question, because eventually you'll find some connection to the formula booklet and then you'll be able to do it. And if I ever forget something, that's the way I make myself remember. So if you see over here, they're giving everything in Leibniz notation, so make sure you're comfortable with like d of dx notation and all of that. So if you look at what this is really saying, what the chain rule is that if you have some function y equals to g of u, and you have u which is equal to f of x, so g of f of x, dy dx is going to be dy du, which means you can just differentiate y normally with respect to u. And then you can multiply it by du dx, which is differentiating the inside as well. So this is what this says. And make sure you can read this and understand what this means as well. Same thing with the product rule. Again, it's just saying that if you have y equals to uv, when dy dx is going to be equal to u
Hello.
dv dx. Yes, hello? You have a question? Or you just said hello? Okay, that's fine. And same for the quotient rule. Again, you should be able to understand how this one works. So that's for the differential, for the derivatives. Again, these are the ones you need to know for SL right over here in the over here, which are all basically everything in the formula you need to know. Just generally how to do them. I would recommend that eventually, with enough practice, you should be able to do this without having to check the formula booklet. Otherwise, you're just wasting too much time. For HL, you need to know a lot more. But again, they're all in the formula booklet, so you don't need to memorize any of these things. Eventually, everything will be in your formula booklet for the derivatives. Sometimes you'll have to be a little creative with the derivatives, like you might get something like sine squared x, and you might think that sine squared x is in the formula booklet, but it's not. And you should be able to use the chain rule for something like sine squared x. So that's all for just knowing general derivatives. I don't think there's much I can go over for like the rules and everything. If there's any specific questions for any questions that you guys have like specifically, then I can answer those regarding for each derivative. But I'm not going to go over like the first principles and how to like products and quotient rules and chain rules, because I feel that like they don't need explanation, but they need a lot of practice, and you guys should be doing practice if you want to get better at them. Next thing is related rates and implicit. So this is specifically HL. So if there's any SL people listening, this is not for you. I just want to know generally how many SL students are there. Okay, there's too many people to even ask that. I'm going to assume there's plenty of SL students, so I'll be doing both anyway. It's okay. So now I'm just going to do this HL stuff, which is related rates and implicit. So implicit is basically a creative use of the chain rule. So if you have something like, let me have a look. I have an example here. This is an insane example for this question. Oh my god. I'm gonna come up with the example right now, just off the top of my head. Here, I have a nice one. I have a pretty example, not Andrew's deathly examples. We do. Let's just make it 3 plus x. Okay. Say we wanted to figure out what is dy dx. If any of you have done geometry or like some kind of like American math course, you'll notice that this is a conic, but that's fine. We don't have to worry about that right now. So let's see how we're going to figure out dy dx. The procedure for doing this is almost exactly the same. You just take d of dx of the entire thing, the whole thing, and then you individually differentiate each term how you're meant to do it normally. So the first term, d of dx of x squared, is just 2x. That's fine. Then the next one, y squared, you would first write 2y, right? Because that's how you differentiate y.
y squared, which would make it 2y. However, you need to keep in mind that y is dependent on x, which means that y is a function of x. So you need to make sure that you're also using the chain rule on y, because y isn't just itself; it has like more inside of it, which you don't know what that is, but you don't have to know what that is. All you have to do is take the d of dx off it. So you take dy dx. So you differentiate the inside. dy dx. You don't have to write down you don't write down the whole thing, try and solve for y or anything. Just write down dy dx. And that's going to be equal to 3yx. Now, actually, I'm just going to remove the 3 because that creates an unnecessary constant that I don't want to even deal with. We're going to use the product rule. So what do? We keep the y the same. Let's differentiate the x. That's just going to be 1, so I'm going to ignore that. Then I keep the x the same, and then I differentiate the y, which is going to be 1, and I would just leave it like that, except y is dependent on x, which means I must make it dy dx right over there. And then the next step is that you want to solve for dy dx. Now you know what dy dx, you have some dy dx's here, some dy dx's here, and what you can just do is try and isolate for the dy dx's. So the way you can do that is just put all the dy dx's on one side, so make it 2x plus 2x minus y is equal to x dy dx minus 2y dy dx. And then we can, after some cancellations and some simplifications, dy dx is equal to 2x plus y over x minus 2y. So I factorized out the dy dx on the right side, and I took out the x minus 2y and put it underneath over here. That gave us dy dx equal to 2x plus y over x minus 2y. Almost every example will be like this, and you should be able to just make sure you always appeal back to the fundamental laws and the fundamental things that you've learned. There's no real trick to doing any of these. It's just about using every single example. Later, I'll be probably, if you have any time later on, I'll probably do another much harder example which is Andrew's examples, insanity. Next thing there is related rates. So this is, let me have a look. I think this is a sane question that is completely possible. And again, related rates is something that is just trying to connect different different rates of change, and using the normal derivative rules and normal derivative calculations to try and figure that out. So I'm going to look at what this try and do this question, and just show you the process of how it's done. There's a small possibility I won't definitely be able to do it, but I'll try my best. We will analyze this question together. Okay, so creative walks along straight path at a speed of 1.5 meters per second. Do you guys want to try this as well? And then I'll explain on the whiteboard, or do you want me to just explain it straight away? Anyone? Okay, you guys can try it, and then I'll explain it right after. I'll give you guys 7 minutes. So I'll be back at 4:18 p.m. I mean, in 7 minutes for my time. And if you need longer, I'll just give you longer. It's okay. Oh yeah, I should show you this cue. That's very stupid of me. Here. I'm posting the cue here. If anyone in SL wants to try this question, just let me know. I'll put it in SL as well.
Hello.
Yes? Who is this person who keeps saying hello? Anyways. Oh my god, this is an insane question.
Excuse me.
Yes?
Is 6 meters the diagonal distance?
Is 6 meters from the point of the path closest to searchlight? No, six. Do you? I'm not sure if you understand what the question means. Then, the 6 meters is not the diagonal distance. It is a horizontal distance from the point of the path closest to the searchlight.
Eight meters is not the hypothesis, by the way. I'm gonna give it 3 more minutes to figure out the problem.
I mean, I can't really look at it. Um, and also, I don't know the answer. I know the method to do it. Oh, okay. So you want to do it like that? Okay, sure. I mean, I'm not giving out prizes, but sure. That's very deep. That's deep. Okay, I'll do the question now. If anyone doesn't want me to do the explanation yet, just like tell me immediately. But I guess I'll show how to solve it now. So the thing with this question is that first of all, it's hard to understand like what exactly is even happening. I'm not fully certain if IB exams will be as like confusing, but generally, if you're able to do something like this, you should be able to do something, basically anything. So let's look at what's happening over here. So creative is here, and he's walking along a path. So I'm going to just label this path like this. And then over here is located on the ground 8 meters from the path. So it's somewhere here. This is a path 8 meters away somewhere. This is flashlight, and so if you just draw a perpendicular to here, it's 8 meters away, right? It's 8 meters away. And at what? And the question is asking at what rate is the searchlight rotating when creative is 6 meters from the point on the path closest to the searchlight. So then now start giving some variables. Now it's asking us what rate is the searchlight rotating. So if we're looking at rotations, that means we're going to look at something. We're going to look at angles, right? So let's just look at what the searchlight is looking at. It looks like that. That's what the searchlight looks like. And we can define this angle right over here as how much it's rotated. And then if we look at what the question is asking us, it's asking us to find d theta dt, which is the change in the angle per time. Which is basically, so that's why it's represented d theta dt. So it's the dt of theta. But then look at what we know. So it tells us that he's walking along a straight path at a speed of 1.5 meters per second. So let's label this x, right? And it tells us that dx dt is equal to 1.5, which means that the change in x for every second is 1.5, which means that every second x increases by 1.5 in this direction and he moves further that way. And what the question is asking us is what is the value of d theta dt when x is equal to 6, which means from this point, which is the closest point, how far, when it's 6 meters away, when x is 6 meters away from this closest point, which is at 8 meters directly away from the flashlight, what is the change in theta? So we want to figure out what d theta dt is when x is equal to 6, given that dx dt is equal to 1.5. Now, the final thing we need is some way to connect x and theta. And now that if you see this, like the way that I've constructed this diagram, you automatically see there is a triangle over here. And the connection that we can make is we have a theta, we have an x, we need to connect them in some way. So we can use the triangle to do this. And we have a known value of the triangle right over here, which is one of the sides, the adjacent to the theta. So we know that the tangent of theta is going to be equal to the opposite over the adjacent, which means that it's going to be equal to x over 8. And hence we can create the connection that x is going to be equal to 8 tangent theta. Now, knowing that we have all of these pieces, we can finally do what's necessary, which is to figure out what dx dt is, to find what d theta dt is by using the definition, by figuring out what the value of dx dt is. And the way we can do this is we can do this. So if we take the derivative of x, we're gonna end up with dx d theta when you differentiate with respect to theta. When you differentiate with respect to t, sorry, we differentiate everything by d of dt like this. Everything by d of dt. Again, we'll also have to use some implicit differentiation over here. So d of dt of 8 tangent theta, so we can just take the 8 outside for now, because I'm not going to worry about that. And if you look at what happens now, it's equal to 8. If you look at what the tangent should be equal to, it's going to give us secant squared theta. And remember that we also need to differentiate the inside, which is theta, because theta is dependent on time. So we end up with d theta dt. Now, we know what dx dt is, right? So we know what dx dt is always. It's always the same value. And we know what, and we can figure out what theta is at any given point. So what we're really solving for is d theta dt. So if we want to solve for d theta dt, we can just write out d theta dt is equal to 1/8 cosine squared theta dx of dt. Now, this is what I did, as I took the 8 down and made it 1/8, and the secant squared theta, I put it made it over here, made it 1/secant squared theta, which made it a cosine squared theta. Now, what are we gonna do? What this says is that if you give me, like, if for this, what this function does is that if you give it some value of theta, which is going to say what its like angle of rotation is at any given point, it can pop out the d theta dt value given the dx of dt value. And we know the dx dt is always 1.5 because that's the change in x at every given point. And we can figure out what the cosine of this is as well. And the way that we can do that is we know that what the triangle looks like at the point that we're looking at is this. There's a theta over here, there's an 8 over here, and the x is 6 away from that point. So this is what our triangle looks like. And if you look at this closely, you'll see it's a Pythagorean triplet. This is 3, 4, 5 in ratio, and it's 6, 8, 10 in that same ratio. So if we can actually figure out the value of cosine squared theta. So if we find what cosine of theta is, it's going to be the adjacent over the hypotenuse, so just 8/10. And we're going to square that. And then dx dt, which is going to be equal to 1.5, which I'm going to make 3/2. Which is then we can do some cancellations. We have 8 squared over 8 times 10 times 2 times 3. You don't have to do these things like this. I'm just being kind of extra, making like everything kind of like cancel out this way, and then just 24 over 200, which is going to be equal to 12 over 100. I don't know why I did that. Which is 6 over 50, which is equal to 3 over 25 there. 3 over 25. 3 over 25. That's what d theta dt is. That's the change that it has. So yeah, that's what that is. Wait. Did I do that correctly? Yes, I did. That was correct. Yeah. Cool. So now I'll just. God. Okay. Nice. 0.13 rads per second. I don't know. What does that mean? It's 3/25. Yeah, 0.12. 0.13. We might have made like some, like, I'm not sure. Yeah, 3/25 rads per second. So, redstone technique was correct. Yep, you were exactly correct. Good job. So that means I was also correct, because if you got a different answer from me, I would be very concerned. Yep, so that's a related race question. Easily, this is one of the hardest related questions. Like, this is the hardest you can get. Like, this is not ridiculously hard, but in terms of IB, this is as hard as it gets. But sometimes it can get really sketchy. So wait, Panic at the Costco. How did you get 0.13? You should get exactly 0.12, with no exception. Like, always. It's... Yeah, well, Aryan, yeah, you need to understand the question. So if you're able to find all the connections, yeah, I gave the answer. Oh wait, 1 second. You're not in the chat. Okay, wait. Let me just go back to what the question says. What the question is and what I did, which is that identified what information has been given to me, dxdt, find out what they want me to find, and then find a correlation between those two variables. And remember, I also had to like figure out what dt is and like try and figure out what's changing, and that's what I'm going to be using to differentiate every single time. So whatever. The most important thing is to find out what this connection is, and then differentiate that connection. Then implicitly, you'll be able to figure out what the derivatives are at different points. Sometimes it's possible they could give you 3 variables. So maybe I could have said, there's another variable as well. There's a dude standing over here, right? And he's like 2 meters upwards and like 8 meters here, and he's shooting. He's like attacking creative from this direction. Like he's also finding a flat light. What is the angle between these two flashlights? It gets more complicated. You can have more variables. You can have more things, but then eventually it's fine. You'll be able to make all the connections between everything. Yeah. Arctan of 6/8 minus arctan of 4.5/8. Where did the arctans come from?
Why is everyone muted?
Because we're in a YouTube VC. If you want to speak, then you just unmute yourself. But for now, just keep yourself muted.
Hello?
Do you have the link to the YouTube stream? It's on the Math HL channel.
And you guys are...
Where did the 4.66 1.5? No,
Hello?
yes, wait. I'm not sure what you did, Panic. But like, just, I guess look at the solution that I have here. Like, I can just post the solution out on the channel 1 second. Wait. Wait 1 second. Andrew's implicit diff question. Oh, that one? Okay, yeah, I'll send that. I honestly don't think this will ever like. Okay, but you guys can try this if you like. I'm not gonna go over it right now. I don't think it's necessary. Yeah, don't make random guesses, please. I have a solution. You can try the solution. That also works. If you're done, can I can like move on and go to the next topics, and more questions probably as well. Do you understand the solution now? Um, Panic. Okay, that's very good. Um, that's related rates. I can probably come up with another question if you would like. Um, okay, I'm gonna move on. And oh, another question. Do you guys want another related rates question? I can send you another one later, I guess. Or you can try on the question bank. But I think I'll move on now because I finished more stuff. Um, okay, so that's related rates and implicit differentiation. Next is finding integrals. So there's indefinite integrals, composition with linear function. Okay, so you should also be.
This guy.
I don't know what that was. Doesn't matter. It's fine. I'm just going to be going over the integration now. So you should be able to integrate all of the functions which you learned to differentiate. And now a few of them are given, right? So if you can see like standard integrals over here, some of them are given. And over here as well, a lot of them are given. However, I find that it's very important to make sure you actually know all these integrals, because sometimes you forget how to you forget how to do them, and you forget what they are, and you really mess up. So for example, these are some that always get me. So one of them is so there's obviously many different kinds of integration techniques. For SL, there's not a lot of integration. The only important things to know for integration is that you can integrate sums differently, and you can integrate like differences differently. So if you had like the integral of x plus y, you can integrate x and then integrate y, and that's going to be the same thing, and add them together afterwards. So what that means is that integrals are linear functions, and they can be compositions, and they can be composed linearly. They maintain linearity. You can also take out scalars, so if you have like a multiple of something, so the integral of 3x is the same as 3 times the integral of x. So yeah, another thing which so that's all that is for all the integrals you need to know. Now for HL, there's a few that always I think that are important to know, because sometimes they come up and then you forget it and then you have no idea how you were meant to do it. So for example, there's some common ones. So there's tangent squared x comes up sometimes, which again sometimes you don't know what to do, but like the way to do the tangent squared x is to remember that you can use a trigonometric identity of secant squared x plus 1 is equal to tangent squared of x, and then you know that then you can integrate them separately, make it secant squared x plus the integral of 1 dx, and you know the integral of secant squared x dx is equal to tangent of x, because that's the antiderivative of secant squared x, because the derivative of of tan x is secant squared x. And that's how you would do something like tan squared x. Another very important one that I think sometimes people always forget is how to do the arcsine of x. So which is the inverse trig functions, how to integrate them, which is not in the formula booklet. You would think it is, but it's not. And it will mess you over if you fuck you over. But yeah, so arcsine of x dx. If you wanted to integrate this, the way you would do it is integration by parts over here, which makes it a lot easier. So the way that you would do that is because for something like the integral of arcsine of x, it's very easy to figure out the derivative of arcsine of x, because the derivative of arcsine of x is given to you. Here, the derivative of arcsine of x is given to you over here, so you're able to differentiate it very easily, but you're not able to integrate it as easily, and that's why you should try to use the chain rule, the integration by parts. I'll explain what integration by parts is just in a minute, like just later. But right now I'm just gonna go over another topic before I go back to solving different integrals. There is trying to find the area underneath an integral. So for SL, all you need to know is that if you want to find the area of an integral, so any curve from some value a to some value b, and you want to find the area between the x-axis and that curve, all you need to do is integrate that function. Say the function is f of x, integrate f of x dx from a to b, which means is to find what the antiderivative of f of x is. So let's say that we integrate it and we find that the antiderivative is f of x, of capital F. You evaluate it, you have a and b, you evaluate b and then a, and that's basically how you do it. And that's how you find the area under a curve. Now for HL, there's also a possibility that you will be given a scenario where you need to figure out what the area under a curve is in the y-axis. So they might give you a function. Say the function is looks like this, right? So say you had some function like this. Now you could say you wanted to find what this area is from between the y-axis and the function. Now how are you going to do this? Let's say this function is x squared. So that's y equals to x squared, right? Now you need to figure out what the area between the y-axis is. Now that's a difficult thing to do, because normally what you do is you would just integrate x squared dx from, like, say 0 to 1, and you just find 0 to 1, you'll be able to find this area. But you want to be able to find this area more easily. And the way that you would be able to find that area is by changing the integrating factor that you're using. Because fundamentally what an integral is a sum of several values. So if you look at what the integrals, if you look back to the fundamental definition of what an integral is doing this. So you have a curve, and they have these little blocks inside the curve. You have these little blocks inside the curve, and each of these blocks has a width of dx, and each of these blocks has a height of f of x. And what so what the area of each of these blocks is f of x times dx. And then we take all of these blocks and we sum all of them from A to B. So any area that we want from A to B. Now we can do now if you want to like figure out how we're going to integrate something, but from the y direction, we can just appeal back to this definition right over here. We draw something. We have some curve, say x squared. We draw rectangles again. Draw rectangles. Each of these rectangles has a height of dy. dy is an infinitesimally small height, and each of these has a height of f of y. So for every given point of y, they have a height of f of y. So it's f of y times y dy is the area of one of these rectangles, and we can integrate this from whatever value we want, a to b. And so that's basically what this says. So when we're looking at functions, as long as you can find f of y, you'll be able to differentiate with respect to y as well. And you should be able to figure out how to do this just by thinking about the fundamental definition, what it means to do this. So if we had f of x is equal to x squared, we need to find a way to define this in terms of y. And the way we can do that is we can try and look at what its inverse looks like. So if we had y equals to x squared, we know that x is going to be equal to square root of y. We look at only the positive value of the square root of y. Like obviously it's going to be a positive or negative square root of y, but the positive square root of y looks at the right side, and the negative square root of y looks at the left side, but we're not looking at the left side right now, so it's okay. We look at the positive side, so we can go with x equal to square root of y. So we know that f of y is equal to the square root of y, and we can integrate this from whatever value we want, a to b, of square root of y dy. And this is how you'll be able to figure it out. So just solve for x, and then you'll be able to find what it looks like in the other direction. It's very much like the inverse, because technically what this represents, if we wanted to figure out what this like is with the y-axis, this is the same question as actually just asking asking what this is, which is y. This is the square root of x, and asking what the area is over here. It's the same question. You can even see they look almost exactly the same what they are. It's because they are the same. It's just finding the inverse. But sometimes it's easier to differentiate with respect to the y-axis, which is why you would do it like this. And also sometimes they might just ask you what is the just the area between the y-axis, not the x-axis, and then you'll need to be able to do this. Yeah. Okay, and you can hear me. Yep, that's a. Oh God. That's nice to see. Okay. Yeah. Okay. Yeah, it is you. It's very disgusting. Okay. Now we can keep going to the. Now we can look at the volume around the curve and the x volume around the curve. What does this mean? Okay, it doesn't matter. Now, what the volume of the curve usually represents in the IB is finding the like if you sweep something around an axis, what does it look like? So for SL, it's only the x-axis because we never look at anything about the y-axis. But this is what it looks like. Say we have any given function. So let's say some function like this, right? And this is from b, from 0 to b, right? Now we want to figure out what happens when we sweep this function f of x, right, around the x-axis and revolve it. And we get like these circular shapes around the x-axis, like this, which is basically sweeping out a vase, which then we can try and figure out what the volume of this vase is. But there's a technique that we can do this. And the way that we can do this is by summing up the volumes at different points of the vase. And how we do this is by looking at each individual point. So let's look again and try and appeal to the definition we used earlier with the summing up several small different things. So let's look at some individual point right over here, right, which has width dx, right, and it has some height f of x, right, and let's just sweep this out. When we sweep this out, it gives us a cylinder. Right, that looks like this, and that cylinder has height dx, and the cylinder has a radius of f of x, and this is all the information you need to find out the volume of the cylinder. So what is the volume of the cylinder? The volume of this cylinder is pi, whatever the surface area of the area of the circle on top of the cylinder is, which is pi times f of x squared, right? And then it is the times the height of what it is, which is dx. And then what we do is we have this cylinder here, but we have all of these cylinders from going from 0 all the way to b, so we can integrate it from 0 to b. And then if we simplify this again, we get pi from 0 to b of f of x squared dx. And that's how you find the volume around the x-axis. for something, and this is immensely useful. Um, because and then you should always be, and the important thing about this is not to memorize this, but to be able to understand what this means. And then essentially you're just looking at summing up all these different points. So summing up all these like like infinitely thin cylinders, to be able to find out what the total volume of the entire thing is going to be. And that's done by using this technique over here. Now, it's also possible that, say for example, I wanted to cut out a portion of this vase. And I had some other function right over here, which is right underneath it, right, this entire thing, because I want to make this vase hollow. It would be a useless vase if it wasn't hollow. So if I have f of x, and now I have g of x over here, which is another function, and basically what I'm doing is that I'm going to take out f of x, I'm going to do f of x, then I'm also going to cut out a g of x amount of volume out of f of x. And the way that we're going to do that now is we're only trying to figure out this, we're only trying to like sweep out this area. This, whatever this area is, the thickness between f of x and g of x, that's how much material we need, like the volume of material we need to sweep it out. And to figure what that is, what we do is we need to figure out f of x minus g of x. So normally, when we're trying to find the integral, if we're just trying to find the area, we would do the integral of f of x minus g of x dx, which is fine. And you might be tempted to just say, okay, if whatever the function is going to be, we can just square this, stick a pi in the front of it, and that's it. But that's not the case. We can't do that. What you must do is that you must treat them as two different integrals. You cannot compose it. And the reason you can't compose this is because the function of like the operation of linearity, where like you can add and subtract integrals, is only true when you're only adding and subtracting integrals. Once you start squaring integrals, multiplying them, like making cylinders out of them, you cannot maintain linearity. So what you need to do is take the take the volume of the f of x portion of the cube, of the vase, and then take away the portion of the g of x part of the vase, which eventually will simplify into pi times the integral of f of x squared minus g of x squared dx. However, it is important that it's this, and it isn't just f of x minus g of x whole squared. They each have to be squared individually in order to find out what the difference is between them, and to be able to sweep them around the x-axis. Now, the exact same thing could be done, but with the y-axis, and it's important that you understand that this also can occur. And ultimately, it is the same principle, the exact same principle. What you're going to end up with is, let's say this is some function, and you want to figure out this portion, and you want to sweep around the y-axis here, you want to sweep it like that. And if you want to sweep it that way, all you need to do is, again, everything which I said before. So you take the cylinder, you make it a cylinder. That's a very bad cylinder, but I know it's just a cylinder. It has height dy, and it has a radius of f of y. And so that what that means is going to be the pi times f of y squared dy, which is dy is the width. And this is the whole. This is what everything's going to be, and you're going to integrate all of these out. And this is exactly the same thing. If you notice, it's the exact same formula. All you need to do is make sure you're using the correct function with the y, and to make sure that you like integrating with the same things. So another thing which I find sort of useful when you're doing this is to draw a sketch of a diagram of what the function looks like. For SL, you don't need to know rotating around the y-axis at all. It's only a HL thing. But anyways, for SL, the questions are going to be simpler. So the kinds of like equations you're going to get are going to be like, you can draw them like quite easily. So you should always draw it when you can. To have a better idea of what everything looks like. Maybe even if you're trying to rotate a volume around an axis, try and just look at the cylinder definition again. Think about what it is. And that'll be a lot better. Rest of I appreciate that joke, but squaring something is not linear, and that will be very sad. Okay, so what is this? I think this should be it. It's just such a bad question, Andrew. It's like, it's fine. um, so that's the integration and volumes under a curve. If you guys have any questions, then can you just let me know? Because I think I went through that fast, and there's a lot that I probably packed into that. Okay, is that it? Okay, cool. So I'm gonna move on to the next part. Kinematics problems. This one's interesting because I can just derive everything that you guys learn in physics. So if a lot of you are in physics, this will suddenly seem so easy for you. Did you say he's so tired? Are you referring to me? Yes, it's been a tiring day. Okay, so the next portion is looking at kinematics. So what I'm going to do is I'm just going to derive everything in kinematics and figure out all the kinematic equations. And here's how we're going to do it. What we're going to look at is the change, how, like, we're going to look at a particle, some particle, right, and how this particle is moving. This particle is moving in some direction, with some velocity somehow, with some changes in acceleration and some forces on it, all these different things acting on it. But what is the case fundamentally is this. The acceleration is constant, and we want to figure out what the velocity is, what the distance is in terms of what the acceleration and velocity are, and how far it's gone and everything like that. And this is how we're going to do it. So if we look at what the acceleration is, now the acceleration is in math is d squared x of dt squared. So what this means is that we're differentiating with respect to time twice on x to be able to figure out what the acceleration is. Now what this means conceptually is that x is the distance, right? So the distance that it's gone. Once we do it the first time, we're going to get the velocity, which means how fast is the distance changing. Then we do it the second time, we're finding how fast is the change in the distance changing, which is the acceleration. And that's why d squared over dt squared x is going to be equal to our acceleration. And we know that dx on dt is equal to our v, and we know that x is equal to what our x is just equal to x, obviously, because x is just like the distance traveled at any given point. And we can differentiate backwards and find the kinematic equations. The way that we would do this is to be able, so say we're only given the first fact. We're only given d squared x over dt squared is equal to a, right? How are we going to figure this out? So the way that we're going to figure this out is by integrating both sides. So if you have something that has a second derivative of x equal to a, if you want to figure out what the velocity is, if we integrate both sides, we undo the operation of a derivative. So if we do this, we integrate both sides. Now this derivation is not necessary, but if you understand it, it would be very useful for you. This is for SL as well, but it could be slightly confusing. Here's what ends up happening. What this integral does on this side is that it basically allows us we do some weird fractional cancellation stuff, which isn't really legal, but it's okay. No one's watching. This is simplifying to dx dt, and on this side we're going to get the integral of a, and in this term, a is just a constant, some constant value, number. So it's going to give us at plus some constant. Now, what is this constant going to be? So let's think about what this says. It says that the velocity is going to be, so dx dt, which is the velocity, is going to be equal to acceleration times time, plus some constant. And acceleration times time, that represents an acceleration occurring over time. So say we started off with zero velocity, right? And an acceleration of 5 meters per second. As time keeps increasing, our velocity also increases, and we keep adding. So every second we add five more to the value of 0. So we get, after 1 second it's 5 meters per second. After 2 seconds it's 10 meters, and then 10 meters per second, and so on. However, the c value, that's an interesting one. The c value, if for example our velocity was already 8, and then we're having a 2 meters per second squared increase every single time. That means we're going to go from 8, after a second we're going to go to 10, after a second we're going to go to 12, after a second we're going to go to 14, and it keeps increasing. So what the c represents is the initial velocity. So what the c represents is v naught in our calculations. So again, if you look at it, v is equal to v naught plus at. Now this is the first thing. This is the first kinematic equation. If any of you have done physics, that's exactly what the kinematic equation is. Okay. 1 second. Interest air is negative or something like this. Oh, y squared. That's a very good question. 1 second. That is a good question. The way that you would do this, 1 second, I'm thinking about it. I haven't actually seen that ever happen, so I'm not sure I can come up. Yeah, I think this is just distracting from what I was just saying about kinematics. I'll finish with kinematics and I'll come back to this and address it. Or Cyan will do it in chat. I'll just finish off with kinematics. So this is what the physics, if anyone's a physics was, this is what the first kinematic equation looks like. And then the next thing that we can do is we can do the same thing we just did to this operation here with the integration. So we can integrate dx dt, and that's equal to at plus v naught, and that's going to give us, if we're going to cancel everything out, it's going to give us x is equal to the integral dt is going to equal to half at squared plus v naught t plus c. And now what is the c? The c is just going to be whatever the initial distance was, because all of this is going to give us the next, any additional distance. The c is going to be the starting distance, x naught. So if you see this equation right over here and this equation right over here, they are the kinematic equations. And you'll be able to solve these things in this mannerism. You don't need to memorize these equations. However, you need to memorize what this technique is, kind of. So if you know what the acceleration is, you should be able to integrate it, and then you'll be able to figure out what the velocity is, plus some constant, which is the starting velocity, and you should be able to figure out how exactly things are going on after you know this stuff. Again, the kinematic stuff is more of just an application of calculus. So in the end, it's not about the physics, it's about the math. And the math is what's just helping you come up with all of the physics. Because at the end of the day, everything is math. Physics is nothing without math. Nothing is anything without math. And if you understand fundamental concepts of related rates, understand fundamental concepts of how things are connected, how things are changing, and what it means to actually have a derivative, the kinematics should come to you. And the kinematics should work. So try, and even afterwards, just try and figure out exactly, try and do this kinematics exercise on your own, again. And if you have any trouble, you can again ask on any of the math channels on IB, but on the server. But try and do this on your own. It really helps, and it really makes you better at doing these, solving these problems. Okay, so I'm going to keep going. Let me see. Optimization. Okay, I'm going to just address this over here, and let's see what Cyan said. Okay. I haven't ever seen something specifically like that question. However, okay, wait. Okay. I'm gonna just address y squared's question just now. I'll copy this image over. So you asked for two things here. First of all, how to solve this question, and you also asked about negative regions and how that works. So sometimes you can have functions that, I'm just going to address the negative region things first because that's a lot more simple. So if we have something like this, right, and you have a negative region over here and you have a positive region over here, who's in the VC doing that? Can you mute yourself, please? Whoever you are. Can a mod just mute them? Is there any mods watching right now? Nope, no mods. Perfect. Yes, exactly, Aryan, you got that. That's exactly what I was going to say. So for when you have negative regions, you need to make sure that you're evaluating like until here. So you make sure you're evaluating. So say this is 0, this is A, and this is B. You evaluate from 0 to A of f of x. And then you also, like you when you're evaluating from A to B of f of x, you know that you're going to end up with a negative value. So you add in a negative value over there right in front of it to make sure it is still going to be positive, so you find out the total area. It's perfect. Now, what I see over here, with the problem I see with this question, is that the tool of integration is that it's able, one second. The tool of integration is that it's able to tell us the distance between the x-axis and something, right? And the problem with your question is that like it's hard to do that right now because this is like crossing over the x-axis and not everything is very clear. Now what I would do is what Aryan said, which is just shift the x-axis itself. So I shift the entire thing upwards until it reaches this point right over here. And I can so that's like by doing a translation. I shift everything. Then what I do is that I split up the region again. So I split this up. Say this is 0, this is A, this is B. I integrate. So say the curved function is f of x, and the linear function is r of x, like Sinai said. I can integrate from A to B and do f of x minus r of x. Now, obviously, I know this is going to give me a negative value, but that's okay. I know it's going to give me a negative value, but that's fine. I can adjust that myself. It's just that you make sure that you know what you're getting is a negative value. You're okay with like dealing with stuff like this. Now, for this part of the portion, again, I would do integral of r of x minus f of x from 0 to a. And that's going to give me this area, and that's going to be that area. But I need to make sure I adjust f of x and r of x to ensure that this intersection point over here is below the x-axis, and everything is below the x-axis, so that I don't have to worry about it crossing over. And that's kind of I think that's kind of the difficult part about that question. However, ultimately, that's not it isn't that different. But then again, I never really see. I've never seen this in an IB paper. At least out of maybe like the 6 or 7 years I've practiced, it's been basically nothing. Perhaps Cyanide. I think I might just be like, I lost track of what you're talking about at this stage. Oh, okay, I see what you're saying. Oh, yeah, that's right, that is correct. Yeah, that's very correct. Yeah. Okay, so, yeah, what I was doing is that I was thinking about everything in terms of in terms of the areas. So what I was doing is I was looking at f of x, the area between the x-axis and then r of x, and like subtracting it, right? However, there's another way to think about this, which is what Cyanide just said, which is using the difference function. That's not a thing actually. That's a made up word, but there's something that you can use. which is ultimately what the integral is a sum of different values, right? And it's a sum. So what we can do is we can draw rectangles between here, like this. So if we draw these rectangles between them, right? Each of these rectangles has a height of r of x minus f of x, right? And then we know that each of them has a width of d of x, because that's the way we do calculus. You put a d of x. Now we sum all of these rectangles, we get the integral. And that's how you do it, by using the difference of them. And you can also find the area that way. Okay, thanks, Cyanide. But you can also do it my way if you feel like that's like more comfortable, I guess. But this way is faster, for sure. And yeah, that's that. Yeah, I feel that sometimes I come up with weird solutions because I just don't think of these things. It's okay. As long as you eventually come up with a solution, it works very well. Okay. Now, the final thing I'm looking at is optimization. So let me just have a quick go at that. I'm gonna see if I can pull an optimization question from here that isn't absolutely horrible. Let's try this optimization question. Another Andrew Great. Again, I think optimization is SL and HL, so I think both of you both should try this. So I'm gonna put this in the HL channel and the SL channel. I'll give you 10 minutes to solve. What this looks? Why are all of Andrew's questions so absolutely hellish? Okay, I'm gonna just say it right now that like, um, it's it's hard, and I have a feeling that my solution might not be the most elegant either. But I will give you a solution, I do have a drawing. I'll give you like a few more minutes to think about it, and hopefully at least you can figure out what the question is asking. Andrew, help him out. This is your question. You have fun. Wait, creative, are you on my stream? Oh my god, I'm... Boom, 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 okay. There, no one saw that. Okay, one more minute, and then I'll explain. God, this is... Jesus Christ. Um, fucking educated guesses. Perfect. Andrew, you can't redeem yourself now, okay? Like, this, you've done the damage. Oh yeah, yours is a better version because it has ladder rungs. Yeah, that's creative. No one asked. Okay, now that we're done with this, it's time. It's time to discuss how to solve this. It was bad. I did not enjoy it, but here we go. So, I drew a diagram. I'm not gonna draw a ladder with rungs. I'm not insane. So here's what it looks like. It has this is 2 meters high. This is 0.25 meters high. I'm setting this angle equal to theta, which is the angle the ladder is set at. And this is the back wall. It doesn't matter what the height of this back wall is. All I know is that, and I don't care what the height of the back wall is at this stage. It only matters whether or not it can actually reach all the way. So the way that I'm going to be able to do this is I need to make sure I can represent everything in terms of theta, which is the only variable that I have. And the optimization question is this length over here. No, I am really bad at drawing. This length over here, which is x, I'm gonna call it x, which is a function of theta, and we need to minimize this, and that's basically checking when dx of d theta is going to be equal to 0. So, what is happening? Why isn't it erasing? Oh, crap, wait. Wait, I need to set something up. This is... Okay, cool. So we're gonna look at getting everything in terms of theta. So the way that I went about doing this is I thought about similar triangles. So I know that this triangle over here, I'm gonna label the points. That's A, B, C, D, E. Tell me at any point, just pop into the VC and tell me at any point if this is absolutely insane. But no, what the hell? You can't just say that I'm insane before I even asked you to tell me if I'm insane. Well, anyways, this is what I did. I realized that I can figure out what AB's length is in terms of theta because I can use the normal trigonometric identity. I can figure out what the hypotenuse of the triangle ABC is because I know one angle and I know this opposite side over here, which is 2. So what I can do is I know the opposite, and I want to find the hypotenuse, so I can use sine. So if I look at sine of theta, that is equal to 2 over AB, right? So, and then what that says, it says that AB is equal to 2 over sine theta. So yeah, I'm gonna move that for now. Now the next thing that I know is that AC, this one over here, is going to be equal to 2 over tangent theta. Because the tangent of theta is equal to 2 over AC. So AC is equal to 2 over tangent theta. And now what I know is that because these are similar triangles, there is this side AC, right, which is being multiplied by some scale to become AE by some factor. So it's being multiplied by some factor in order to become AE. And I know that because they're similar triangles that AB, which is 2 over sine theta, must be multiplied by that same factor in order to get AD. And AD is what I have to minimize. So let me just check in Discord if that's the best way to do this. Yeah, you guys are just memeing. Nice, nice. Did you just say this one is easy? This isn't easy, Andrew. Are you insane? Easy to mark. Okay, good. Now I need to figure out what this factor is. And the way I can figure out that factor is dividing AE by AC. So I can divide AE by AC because I know that AE is just AC plus 0.25. So I know AC is 2 over tangent of theta plus 0.25 over whatever AC is, which is 2 over tangent theta. And now I know that this is the scaled factor that I multiplied by in order to get AE from AC. That's the same thing I can multiply AB by in order to get AD. So I can multiply this by 2 over sine theta and simplify everything from this, and I'll be able to figure out what the value of AD is. So I'm just going to pop in and do that now. So I get 4 over tangent theta plus 0.5 over 2 sine theta over tangent theta, which the bottom is equal, sine thetas will cancel out because the tangent theta is equal sine theta over cosine theta. So this will become this will just become 2 cosine theta. 2 cosine theta at the bottom. And I'm also just gonna make it a what else can I do over here? I'm just thinking of all the ways I can simplify this. Cause I really don't like how this looks right now because of the fraction. Actually, you know what? I can simplify this and just like make it like 4 cotangent theta plus 0.5 over 2 cosine theta. This is what this length is, this maximum length over here. You need to minimize this, and that's what the question is asking. Divide by cosine. Oh yeah, I can divide the top and the bottom by cosine. No, I can't divide the top and bottom by cosine. It doesn't work. That doesn't work very well. Wait, can I do that? Divide by cosine. Yeah, I can divide the top and bottom by cosine. That's very smart. Thank you very much. Thank God. 1 over 2 cosine theta over 2. Perfect. Thank you so much. Two sine theta plus 1 over 4 cosine theta. Here, this is what the function looks like. You just need to figure out when that's equal to 0. Perfect. What is happening here? That's where? That's a sign. Everything, I never wrote cosecant down. It's cosecant? Where's the cosecant? Oh, yeah. Yeah, okay, I got it. Yeah, I know what you're talking about. Yeah, that's a cosecant. And that's our function. I am not in the mood to. Actually, let's do it. It's fine. It's fine. Actually, in the spirit of using the indicative cosecant theta plus 1/4 secant theta, I'm going to differentiate this. Differentiate this. What is the derivative of cosecant theta? I'm not bothered right now. Ah, my God, this is disgusting. Derivative of cosecant theta is negative cosecant theta cotangent theta. Plus 1/4 secant theta derivative, which is, I think it's secant theta tan theta. Okay, that's secant theta tan theta. And I need to set that equal to 0. When this equals to 0. God, this is horrible. What the hell? Andrew, am I right? Andrew, is this even correct? This can't possibly be so disgusting. You can't have made such a bad question. Just no response. Yeah, I can graph it and get the answer, but crap, this is just. Blah. Yeah, that's what it looks like. Nice, amazing, beautiful question. I'll just pop that into here. There, that's what it turns out to be. What an amazing question. Here, the value is 1.107. Thanks, Andrew. Solve with calculator, 1.107. Dare to try to solve this without a calculator. You can probably do it, but this is what you've done. It's 1.107. I did do the questions myself, but what is this? This is just ludicrous. Okay, just for everyone's information. Normally in IB questions, at the end, like towards the end of the question, it starts getting easier, which indicates that you're going in the correct direction. However, in Andrew's questions, it doesn't work that way, because as you keep going, it just keeps getting harder. And that's not how it works in IB. So everyone, it's okay. It's okay. Screenshot my working? Yeah, sure.
No, actually, redstone, like, they're not actually a representation of reality because on the one hand, they're not just like normal questions, they're just ridiculous. Like, when is a ladder like this? What kind of a ladder is this? Like, you have like the weirdest measurements for this ladder. Like, it's fine. It's okay. We can move on from this now. We're done with optimization. It's probably the hardest optimization question I've ever seen. But optimization. Essentially, well, yeah, sure, but in reality, like you're solving a problem, but like it's in a restricted amount of marks. You're not able to do these things. It's ridiculous. Okay, yeah, go back to the graph here. That's what it looks like. Yeah. No, that says 1.107. Oh yeah. Okay, wait, you just used the wrong value. It's 4.249. It's 4.249. It's the next one. No. Wait, one sec. What theta solves for is the radians. So what theta is the radiant angle. So what you need to actually do is you need to again go back and plug in theta to find out what it is. So you need to plug 1.107 back into the entire like thing in order to figure out what it is. That's why. No one likes you, Andrew. Okay, there. We're done with that. Next. Integration by substitution, integration by parts. Yeah, what? No, I think I'll choose to do this because this makes me having you tortured is nice. So I'm gonna copy paste the docs versions of all the questions. Let's do some integration now. Yeah, I don't think a substitution is there. Yeah. Okay, so let's try this. I'm not gonna do substitution first. Let's do an integration by parts. Which is okay. So integration by parts. Here's a really nice example of integration by parts I always use. Arc sine of x dx. How you integrate this is the integral of arc sine dx. By the way, SL, I think I'm done with LSL content. So if SL wants to just go, it's fine. There's only HL now. Yeah, okay. Arc sine x dx, that's going to, so the way that we would do this is that this is obviously you're not able to just normally integrate it. So you know the derivative of arc sine x is way easier, so this is how you would do it. So you have u, v, du, no wait, that's not how I do it ever. U, du, v, dv. And I set dv equal to 1 dx, and then I know that v is equal to x. I make u equal to arc sine of x, and then the du is going to be equal to
1 over the square root of 1 minus x squared. Hence, I know that I can use the integration by parts, so uv is equal to x arc sine x minus the integral of v du, which is x over the square root of 1 minus x squared dx. Now, this is the simple part, so this is the integration by parts done. Now we know we can solve this integral quite easily because we can use a u substitution. So now we've already used integration by parts right over here, which is, again, this is in the formula booklet. So if you ever forget what integration by parts is, just go to the formula booklet. This is written there, exactly how to do all of this. But always make sure that whatever, like, if you're not able to integrate something correctly, make sure that you like put it in the correct place into one of these values so that you're not just like differentiating something that's like ridiculously hard to do, or like integrating something that's ridiculously difficult to integrate. Always the aim is to make it simpler or to make it easier for you to do. So this integral can be calculated by using a u substitution as well. So the way this would work, we can make u equal to 1 minus x squared, and in that sense, du dx is going to be equal to negative 2x. So du is equal to negative 2x dx. Therefore, I know that x dx is equal to negative half du. So I can change this this entire expression into x arc sine x minus half, minus half, so it becomes a plus, the integral of 1 over the square root of u dx. Right, and this is just the same thing as x arc sine x plus half. Oh, this is du, by the way. Sorry about that. Half integral of u to the negative half du, which is a very simple integral to do because it's just using the power rule. So we can make that integral of u to the half. U to the half. So what you can just make that x arc sine x plus half half times u to the half, which then simplifies into x arc sine x plus 1 over 4 u to the half. And we know that u to the half is just, u is just 1 plus x, 1 minus x squared, so it's 1 minus x squared, and squared of 1 minus x squared. So there, I did integration by parts, and we also did integration by substitution. And anything else here? What else is happening here? I don't use the tabular method, by the way. I've never done the tabular method, and I don't know the DI method at all. So I will not be getting to the tabular method because I do not do that. And I don't find it very useful either because in IB, they at maximum have like 1 or like 2 integration by parts. It's trivial, it's very easy to do. You do not have to worry about it. Also because the tabular method isn't really completely set in my mind at this stage. Like, okay, I don't mean it's trivial, I just mean that it's the same thing applied twice, and that it doesn't, you don't need to be using, you don't need to use some special technique to do it. So yes, you can just integrate by parts twice. Okay, cool. Oh yeah, that's right. Wait. Panic had a great point over there. I'm an idiot. This is just, that's 2, and then this cancels out, and there's no 1 over 4 here. Yeah, I'm the king of making dumbass mistakes. I don't even know if I want to go into Andrew's like integrals at this stage. Like, what is this? Like, this is ludicrous. Like, you know what? Never mind. Okay, you know what? We're gonna do this instead because I'm not gonna do more of Andrew's integrals. I'm not gonna satisfy myself to that. We can try with this question right over here. I'm assuming there's no more SLs because it's not. This is like far from HSL anymore. We can try this question. This seems fun.
Okay, I'm gonna explain it now. So no, creative. It's just you. You're really stupid. I'm sorry. Everyone else here, top-notch quality. Okay, I'm gonna explain it right now. Let's see. Have fun with this one. Oh shit. First, let's just find the indefinite integral of x f of x dx. This can be done using integration by parts. Note that there's a double derivative over here, but with integration parts we can get rid of that. We can make that better. And the way that we can do that is this. You can look at u du and v dv, and we can make dv equal to double derivative of f of x, and then we can make v equal to the single derivative of f of x. We can make u equal to x, and then this equal to 1 dx. And eventually, that's going to give us a x f of x minus the integral of f of x. Integral of f of x df dx dx, as so, and that gives us x times f prime of x, and because the integral of a derivative is just go backwards, so you're going to end up with f of x right over here. And then you evaluate that from -2 to 1, and you get 1 times f derivative 1, f derivative 1 minus f of 1 minus actually plus 2 f prime of -2 plus f of -2, and then I can use all the values from the start of the question. That gives me f prime of 1 2 minus 3 plus 2 times 5 plus -3, which is minus 3. That's 10 plus 2, 12, 12, 12 minus 6 is equal to 4. There we go. 23? 6. Wait, what do you mean derivative of derivative of just go backwards? I mean that the integral of a derivative is just equal to the original function. That's what I mean by that. Yep, I think that's the last one I'm gonna do. You can do more integrals in your free time without. You guys can do more integrals in your free time. A British fundamental theorem of calculus. Indeed, that's exactly what it is. I mean, they never actually ask you to state the fundamental theorem of calculus. In most of math, they never actually ask you to state anything unless you're like in the options or something. So you don't ever have to worry about that. Regardless, I think that's the end of the session. That's all. No, it's okay. It's okay, Rated. Can we just not? Okay. I'm not using a trig substitution creative. I'm not using a trig substitution. I would use my own technique. I can give you guys 5 minutes to do this and then I'll do it as well. but I doubt that I'll do it the intended technique. Do you guys want to do this integral, or do you just want to do it on your own, or are you just trying to make fun of me? Except when there's an easier method, Andrew. That's what I was gonna, you just don't know the easier method. Okay, here we go. Here's my time to shine. Okay, this is my time to shine. Okay, I guarantee you my method is better. Here's the integral. Squared. Okay. I'm just gonna rearrange and write this. I'm gonna pull a big brain move here. And this is what I'm gonna do. I'm gonna make this x plus 1, and I'm gonna put that over square root of negative x squared minus 2x plus 3. That's a better way to write it, and then I can take away the 1 over square root of 3 minus 2x minus x squared. Okay, any comments about that? Okay. Now wait and watch. Now wait. Let's do this right side integral first, because it's beautiful. It's nice and sexy. Here's how we do it. It's equivalent to the integral 1 over the square root of we can simplify this into if you take a negative sign out in front of it, we can make it x squared plus 2x minus 3, which is equal to 1 over the square root of negative x plus 1 squared minus 4, which is equal to the integral of 1 over the square root of 4 minus x plus 1 squared. And if you notice, that's equal to 2 squared over there. Beautiful, right? Because now you can pop over to the okay, if you look at the integral in the HL, look at the integral right over here. You have some special integrals here. Here, right, this one. It's the arc sine of x over 2. Beautiful. Except, one second, let me think about this. Arc sine x over 2. Wait a second. I think it works out exactly the same way. Yeah, this is equal to arc sine of x plus 1 over 2. I don't have to worry about the x plus 1 because x plus 1's derivative is just equal to 1, so it's fine. It doesn't really affect much. So that's equal to arc sine x plus 1 over 2. That's the first part. Here's the next part. This little thing over here. This is where it gets interesting. We can set u equal to negative x squared minus 2x plus 3. What are the comments here now? Andrew, they don't do that in like IB, okay? Like, what's up? Like, whatever. Okay, it's fine. U is equal to negative x squared minus 2x plus 3. Du is equal to negative 2x minus 2 dx. Note, now this is equal to, du is equal to negative 2 x plus 1 dx. And if you put the negative half in front of here instead, we can now substitute this in, and we get the integral of negative half du x plus 1 dx. We get 1 over the square root of u du, and a negative half right in front. Now this, there we go, 1 over square root of u, that's the same thing as u to the power negative half. That's u to the half, that's 2 u to the half, which is the integral. That's times negative half du. That's equal to negative u to the half. Why did I put a du there? Now I'm adding differentials when I don't need them. Negative u to the half, and then popping in from up here, we have a minus of the arc sine x plus 1 over 2. That's minus arc sine x plus 1 over 2. And there we go. That's the integral. See? So that calls the end of it. I understand there's this whole like way to like differentiate, like to use like the use a trig substitution, but you really don't. You don't need to. It's just, there's no real point. You're just wasting your time. Because at the end of the day, the trig sub is not about what's faster. It's what we understand. Because whatever you understand more is what's faster. And the trig sub is just not efficient over here, because it's too convoluted. It's much easier to do this one. How did I do it? I put it in the video stream. So, wait, I'll show you. Okay, I'm gonna end the live stream now. That's the end of the live stream. We can still stay here and chat about the stuff though.